Morning, everybody. It's lovely to see you all in such great numbers here. What a lovely evening it was last night. Thank you so much to Nicolas, to Alain, and to everybody else who worked so hard, and all of the wonderful people behind the back who are doing all the hard work. It was absolutely fantastic and most enjoyable to see Paris from the river. So it's my great pleasure this morning. My name's Sarah Springman. I'm officially down as being from ETH, but I'm actually based in Oxford now, so lovely to be here and to be able to introduce Pierre Schmitt, who is speaking first of all. He graduated from École Centrale de Lyon and then went on to the Université Scientifique et Médicale de Grenoble, where he obtained a master's degree in soil mechanics. And then his life was devoted to Soletanche for the next 41 years. And he was obviously somebody who came all the way up through the company to the very, very top to be the group engineering and scientific director, but he went via Egypt International and all sorts of other, the Soletanche Bachy France office, and he has done some amazing things which we're going to hear about in his paper. So hand over to you now, Pierre. French practice for design of embedded walls, history and background, overview of limitations of different models and calculation approaches. Pierre, the floor is yours. Thank you very much.
Thank you very much for this introduction, and good morning, everybody. And the objective of my conference this morning will be to provide a very quick overview of our French practice for the design of embedded retaining walls, which is a practice that obviously is common with most European countries with which we are sharing Eurocode 7. But there are still some national specificities, I would say, for which I will try to provide some background. So very quickly, how can we characterize our French practice for design of embedded walls? For ultimate limit state design, I would say that we preferably use traditional approaches based on safety factors applied to the global earth resistance according to the so-called RFA, the resistance factor approach. Preferably two partial factors being applied directly to soil resistance parameters, friction and cohesion, in line with the MFA, the material factor approach. For calculation themselves, we use significantly traditional models, of course in combination with numerical models as necessary, but not only numerical models. By traditional, I mean models relying on the use of earth pressure coefficients in line with Coulomb's tradition and complemented by the plasticity theory, finally resulting in the use of Kako, Kerizel, and Apsis tables for earth pressure coefficients that are still part of our daily practice. These coefficients were initially implemented within the frame of limit equilibrium models, but during the 70s, these models were progressively complemented and then replaced by subaggregation software that also make it possible to consider relative displacements of the wall. So clearly, it might look strange that France, that's a country with rather a revolutionary tradition, looks a little bit conservative, still relying on traditional models and approaches. And maybe we could say that our progressivism is partly concentrated on the intense use that we make of geotechnical monitoring and, as necessary, the observational method, which are a way for us to, of course, to deal with geotechnical hazard, but also to get databases of similar experience to refer to for projects and also get a better understanding of models and of their limits and the parameters, in fact, associated with the models. And finally, we came to an important conclusion. I'm sorry if I provide my conclusion in the introduction, but at least doing so, I'm sure that even in case I'm short of time, I will have at least delivered my message. And this conclusion is that indeed, obviously, it is difficult to find a universal model that would apply in all circumstances and provide all answers. But on the other hand, it seems that all existing and traditional models are relevant, provided that they are used within the limits of their validity range, which is maybe the most difficult thing that we have to assess in practice, because we are never very well aware of limits of models. We do not communicate enough on that. And clearly, this morning, I will try to focus on the limits of the models we use. A quick mention of our practice for soil investigations. As everywhere, of course, we are combining lab tests and in-situ tests. I would just like to mention these two specific French tests that are first the well-known Pressiomètre developed by Louis Ménard, resulting in measurements of the Pressiomètre modulus EM and the limit pressure PL. It's important to remind that as EM is measured in a purely deviatoric stress path, what Ménard called an extension stress path, to which some categories of soils may be more sensitive than others, some of them being potentially affected by early plastic strains, it was necessary for Ménard to introduce the structure coefficient alpha that may itself be correlative to result of cyclic tests, as shown by Jean-Pierre Baud and by Yves Canepa, and finally resulting in the reference modulus EM upon alpha that we currently use for projects, and that better represents, I would say, typical odometric or triaxial stress paths, or more generally, stress paths including a significant isotropic component. Less known is the phycometer developed by Gérard Philippona that completes the measurement of pressure exerted on the borehole wall by a measurement of shear resistance, so that it's possible to have an in-situ measurement of these two important parameters in Coulomb's criterion that are friction and cohesion. And good news is that this test should be, in the near future, the object of an international ISO standard, the phycometer borehole shear test. Well, now, getting to the heart of the matter, I will briefly mention this very important ultimate limit state for embedded walls. That is what Eurocode 7 calls the rotational resistance, that just consists in checking that the embedded part of the wall is sufficient to mobilize the required level of passive resistance. We are typically, currently doing that, just checking that the ratio between the available resistance derived from passive earth pressure coefficients and the mobilized resistance derived from SLS, serviceability limit state calculations, is not less than a ratio typically in the range in between 1.5 to 1.9, in line with the requirements of the resistance factor approach. And this is indeed different from the MFA that represented on the right, that requires to produce ULS calculations, including partial factors applied to friction and cohesion, so resulting in both reduction of passive resistance and an increase of active pressures, and finally, a significant effect, of course, on ULS solicitations and in structural design. Of course, this was the object of many discussions during the Eurocode process, and many comparisons were made. I would like to present one that was provided by Christophe Baudouin in the example of a sheet pile wall with two levels of anchors, where, for which a comparison was provided between the blue curve that represents, the blue curve represents bending moments in derived from SLS calculations, so without any partial factor being applied. The red curve is derived from the blue curve by applying a multiplicative factor of 1.35 in line with classical structural calculations for ULS design. That is our practice. And the green curve derives from MFA with partial factors of 1.25 applied to friction and cohesion, for tangent of the friction angle and cohesion. And we can see that, of course, the effect is very significant. Even if it needs to be emphasized that structural codes for steel structures make it possible and even recommend to consider plastic hinges within the structure of the wall to create some redistribution and finally reduce these huge bending moments. But unfortunately, this is not common practice for thick concrete structures such as diaphragm walls, although it is, in that case, of the utmost importance to avoid excessive densities of steel reinforcements that could prevent a proper concrete placement under bentonite mud. And this may explain why, in fact, we definitely prefer the red curve compared with the green one. Even if we are, of course, aware that 1.35 is not such a high safety factor to deal with all geotechnical uncertainties, so that we need to be very careful when considering properly geotechnical limit states. And thinking about that is provided by this series of drawings produced by the Paris software that was developed by the Soletanche Bachy company in order to generalize Coulomb's method to derive, in fact, the active pressure on the wall from consideration of the most critical failure surface within the soil. And we can see that on the left, the critical failure surface is a plane surface, as initially considered by Coulomb. And when progressively increasing the inclination of the slope on top, we can see that we move towards something on the right that looks more circular or spiral shape. And we can anticipate that if we continue like that, we should not be very far from an overall instability. So a question that rises is when moving from the left to the right, how can we be sure that we are not somewhere crossing the borderline that delimitates the validity range of conventional models we use, relying on Coulomb's method or active earth pressure coefficients, since there is, in any case, an implicit assumption that is that the overall displacement is equal to 0, or at least is small enough so that we can be sure that there is no risk of having a soil mass moving toward the wall and possibly preventing decompression and eventually entering a passive state instead of an active one. And this is a limitation that the model itself is not able to predict, since it doesn't pay any attention to overall displacement. So maybe in practice, the only indicator that we have to check that is the safety factor relative to overall stability. And because, of course, the higher the safety factor, the lower is the overall displacement. And maybe this could explain or maybe justify why traditional RFA that we apply in France requires relatively high values of the safety factor in the range between 1.3 to 1.5, which is sometimes not very well understood by our European colleagues that rely on the MFA that only requires 1.25 safety factors. But maybe this could be justified on the fact that finally we use implicitly safety factors as indicators to check that we are far enough for the validity limits of the models we use. But this is, of course, a little bit difficult to translate into Eurocode language, which explains why this is still subject to many discussions. Finally, to conclude with ULS practice, in France we do not hesitate to consider different design approaches for different structures. For instance, for nailed retaining structures that are built during excavation, which generally may be not so high safety factors and non-neglectable displacements. Clearly, the conventional models do not apply here, and we rather make the design by reference in the same way as for reinforcing elements in the slope stabilization project. And clearly, it seems relevant here to apply MFA and making the structural design directly linked to the results of overall stability calculation with partial factors on it, which is obviously different from a situation for embedded walls, for which we are farther away from geotechnical limits, and conventional models generally apply, and in that case, we will preferably use the RFA in order to better optimize the structural design. So this is anyway our philosophy. I would like to mention now other limitations of traditional models, in addition to limitations relative maybe to overall displacements. One of them is relative to the length of anchors. Here, the sketch here refers to the Kranz method, that is a German one, and not specifically French. But the principle is to ensure that the anchor force applied in the soil is far enough from the wall to be dissipated by internal shear resistance within the soil without generating an interaction with the wall and possible increase of active pressures considered in the design. And if the criterion is not met, it does not necessarily mean that we are reaching an ultimate limit state. In fact, it's not really a safety factor that one requires, but we understand it as an indicator that if the criterion is not met, we need just to use a more sophisticated model to take account of the interaction that traditional models cannot consider. The example typical is this project here on the right that takes place in Monaco, which is a location where it is forbidden to drill anchors under existing buildings. So that clearly the anchors on the top here are much too short compared with the great depths of the excavation, so that clearly we had to use finite element calculations here, and also obviously adjust the construction sequence by undertaking the deepest excavation stages using a top-down sequence, while the upper slabs were simultaneously constructed in order to take the part of the reaction that the short anchors themselves were no longer able to equilibrate. And finally, geotechnical monitoring showed that the model was realistic, which would obviously not have been the case with only traditional models. Another limitation that Emmanuel Bourgeois already mentioned yesterday is relative to arching effects. Here, this example here is taken from the construction of the first line of the Rennes Metro. We have here a 20-meter deep excavation with a 10-first meter taking place in fields and alluvium material. We used here a conventional Berlin wall with 2 levels of rigid struts. And the 10 last meter take place in weathered rock, using only shotcrete nails, so much less rigid retaining structures. And in such circumstance, it would surely be a mistake to rely only on traditional models, because as finite element calculations show, there is a significant displacement at the level of the weathered rock, and resulting in a vertical arching effect, and finally mobilization of passive pressure behind the wall at the level of the second layers of struts, and with an increase, of course, of the reaction taken by this level of struts. And here, clearly, we have presently no indicators for that other than common sense, I would say, that recommends when using traditional models, more especially when there is no water, so that all the action comes from the soil itself, to avoid mixing to different rigidities of supports, as in this project, or when walls are flexible, to avoid excessively high spans between 2 successive levels of supports, more especially when supports are passive, because in this case, traditional models will not consider the possibility of passive pressures outside unless supports are pre-stressed. So this is indeed a limitation that also needs to be considered. Now, looking at what occurs on the other side of the wall, yeah, I must confess that I feel a little bit confused to present in front of scientific assistants as today such a basic model as the subgrade reaction one. That consists in just representing all the stress-strain behavior of the soil on the passive side in between plastic limits by a single spring coefficient that is supposed to represent everything, based on assimilation of the soil to independent springs. That is obviously not very realistic. And based on the linear elasticity theory, being aware that soil behavior is generally neither elastic nor linear, it comes as shown on the right that the K can be proportional and even of the order of magnitude of the ratio between the soil modulus ES, whatever it is, and the ice A upon which soil structure interaction develops, which is itself traditionally expressed as being 2/3 of the total embedded depth based on a supposed rotational kinematic at the basis of the wall. And, well, indeed, how come that France, that's a country of Coulomb, country of Descartes, of rational thinking, still relies on a non-scientific model, the validity range of which is often considered to be not very far from zero? And indeed, the answer lies in the geotechnical monitoring we undertook from the beginning of the 80s that show, as in this example taken from the construction of the first line of the Lille Metro, that this model may provide good results compared with topographic and inclinometer measurements. But of course, major adjustments are necessary. First of all, the assumption A equal to 2/3 of D, we can see here that it may be relevant for the last stage of excavation, but not for the intermediate ones, because for the intermediate ones, the embedded depth is much higher, although the interaction ice A seems to remain of the same order of magnitude. Also, initial predictions, estimations by classical authors, such as Terdaghi and Ménard, were significantly underestimated. So we had a lot of back analysis were necessary before coming to a synthetic expression. Of course, results are very scattered, but an average figure is provided by this formula, K equal 3.6 times our reference modulus Cm upon alpha divided by A, which is about 3 times higher than initially proposed by Ménard, probably based on an extrapolation of databases, mostly relative to foundation structures. But what is difficult here is that at design stage, we don't have inclinometers to provide a relevant value for A. So we have to rely on the so-called theory of beams resting on elastic supports, beam on spring models. And assuming, for instance, that the embedded part of the wall may be assimilated to a vertical beam, the object of which is to transmit to the soil under the excavation the overall forces exerted by the upper part of the wall, then the theory may provide an analytical expression of the interaction height A, which is in the range of 1.5 times the elastic length, which is itself traditionally expressed as 4 times the bending inertia of the wall divided by K to the power of 1/4. And so finally, A depends on K depends on A, so mixing these expressions, we can get into an expression of A that is surprisingly and generally in good agreement with inclinometer results, and an expression of K that only depends on the soil modulus and the bending inertia of the wall, and that we currently use for projects with reasonably good results, as shown in this example that was taken in a project in Coulomb near Paris, for which we were very happy to have a very dense and high quality soil investigations, of course, and but we are very happy to have, without any back analysis being necessary, a perfect matching between results of calculations and inclinometers in all monitored sections. There were 2 different monitored sections, and in all stages of excavations, processing of front course, and so on. So, of course, those who attended my previous conferences will say that I always present the same example, and they are perfectly right, because I have no other example that provides so perfect results, of course. But it is important to notice that this may occur, so that there is no objective reason to reject this model. Now, question, as I said at the beginning, question is, what are the limits of the model? Because obviously there are limits. For instance, limits may come from deep water pressures. For instance, it may occur that the embedded part of the wall is essentially subject not only to mechanical forces, that is in the general situation shown on the left, but mostly to hydraulic pressures, more especially when the wall had to be deepened to reach an impervious layer at depth for water tightness reason, or when we are making pumping tests without any excavation. In both cases, we can observe that A is no longer dependent on L0, but indeed may reach in practice the total length of the height of the wall, or the 2/3 of it, anyway, resulting in a much lower values of K that predicted by the formula. On the contrary, excuse me, it may occur that for short and rigid walls, the elastic length L0 may be huge compared with the depth, the height of the embedded part of the wall. So in that case, we clearly have to limit the theoretical expression of A to the physical height of the embedded part of the wall, or the 2/3 of it, as proposed by Ménard, and finally resulting this time in a higher value of K. For cut and cover sections, it may occur that the 2 facing walls are close to each other, possibly resulting in an interpenetration of passive wedges, resulting in an underestimation of passive resistance by both passive host pressure coefficients and also by the subgrade coefficient, which was sometimes shown to be reasonably approached by just the Hooke's formula, considering the shortening of the trench of soil comprised between the 2 walls, so another evaluation may be necessary. Another limitation may come from the time effects. In Coulomb, a project where we were happy to have very good matching between the results and the measurements, we were also happy to have long-term measurements, which doesn't very often occur. And we could see that 1 year after the end of excavation, there had been, of course, some significant creeping of concrete that had been considered in the calculations, but we also had to divide by 2 the coefficient of subgrade reaction, which had not been really anticipated and was probably due to the creeping of the alluvium material under the great forces exerted by the permanent anchors. But we still need to progress, of course, on our knowledge, more especially that we have to confess that our databases are mainly relative to short-term conditions, because unfortunately, geotechnical monitoring generally stops after the construction is finished. So we would need more long-term measurements, of course, to progress. But finally, you could say, okay, let's take the point that traditional models may provide good results, but isn't it a little bit complicated to be always aware of the limits, always aware of physical mechanisms involved in the project itself? And wouldn't it be more simple to systematically use numerical models that take account of everything, and you just have to introduce data into the computer and wait for the results? So clearly in France we do use, of course, numerical models, but we're not prepared to use only numerical models for various reasons. One of them is that, of course, these models in practice are not so simple to use for many practical and geotechnical reasons. There are also some limitations. One of them is relative to ultimate limit set calculations, because generally numerical models are used in combination with MFA because it is much easier to place partial factors on friction and cohesion. But for reasons I tried to explain, we are rather reluctant to use the MFA systematically. Another limitation is relative to anisotropy, because there seems to be a consensus in practice to neglect anisotropy, because that will necessitate more sophisticated models and parameters to measure. But it may occur that alluvium soils are significantly anisotropic, and which may explain why sometimes we were a little bit disappointed by comparison with geotechnical result of geotechnical monitoring, more especially when checking for both horizontal and vertical displacements. So this is also a small limitation. Another limitation that was also mentioned by Emmanuel Bourgeois is relative to linear models, to the point that during the Eurocode discussions, it was sometimes considered that it would be wise to prevent the use of linear models for excavation projects. The reason may be understood based on this example that was taken from construction of the second line of the Cairo metro, for which we could see that purely linear calculations have significantly over-predict the heave due to excavation, that is a huge unloading. And finally, correct orders of magnitude compared with measurements could only be provided by non-linear models or just by empirical formula. But now, is it a reason to reject linear models when just checking for horizontal deflections and bending moments? It would be a paradox to accept subgrade reaction and to reject finite element models, clearly. So in both cases, in fact, the most important question to ask is which equivalent modulus should we use to get realistic results with linear models? Thinking about that is provided by this stress-strain relation in the case of a triaxial test, in which we tried with Michel Gambin, who is a well-known Pressiomètre specialist and was one of Ménard's colleagues, to represent what in Ménard's mind could have been the EM upon alpha reference modulus. And we came to the conclusion that it should be some kinds of tangent modulus starting from the initial conditions that are in situ conditions, as for a Pressiomètre, of course, which needs to be distinguished from the E0 initial modulus that characterizes the soil sample when it has just been isotropically reconsolidated without any deviator being applied yet. And for deviators, we can have, when soils are normally consolidated, of course, a rough estimation of the deviators. In K0 conditions, we can derive it from the Jackie formula. In plastic conditions, of course, from the Coulomb's criterion. And finally, with this very rough calculation, it comes that the at-rest deviator is equal to the limit deviator divided by 2, which is, although it is very simplified, interesting because it makes a link with the E50 modulus, that is a reference modulus in a well-known international finite element software. And if we assume, in addition, that the stress-strain behavior is a hyperbolic one, it comes that the tangent E50, that is our reference EM upon alpha modulus, is equal to the secant E50 divided by 2, which may explain why, in practice, when comparing results of nonlinear calculation, for instance, with the HSM model, with geotechnical results, we get rather good matching using values of E50 in the range of twice EM upon alpha. That tends to demonstrate that Michel Gambin's representation is rather relevant. But also interesting to notice is that starting from the same initial conditions, if we consider no longer a primary loading as for a foundation, but an excavation project for which we at least partly go into an unloading, reloading process with unloading due to excavation, reloading to do mobilization of passive earth pressure, But this is a situation in maybe you can understand why linear models may be realistic for unloading, reloading stress paths, which might also partly explain the success of subgrade reaction models. And we may understand why it is necessary to consider higher values of the equivalent modulus that should lie in between the E50 or 3 times E50, that is generally considered as the order of magnitude of the unloading, reloading modulus. And between 2 and 6 times the EM upon alpha, an average value of 4 times generally provides realistic results comparing geotechnical monitoring with calculation using only a linear model. And what's interesting is that this order of magnitude is exactly the same that is implicitly considered in the formula we used for the coefficient of subgrade reaction. So that this seems rather consistent. Although it must be emphasized that for significantly over-consolidated soils or soil with microstructures, as I said yesterday, we may have to consider higher values of the equivalent modulus, both for excavation and for foundation projects. But finally, my conclusions are, finally, traditional and numerical models seems to be consistent with each other. No war seems necessary between supporters of models. The same can be said of MFA and RFA design approaches that are all of them relevant and useful. It would probably have been a mistake to reject or to favor one of them, as it was sometimes considered during the Eurocode process. Of course, geotechnical monitoring is very important and necessary to still improve our knowledge of models and of their limits. We still need to progress on that. And my personal conclusion is that maybe standardization work, such as Eurocodes, should be aimed not maybe at looking for a universal geotechnical practice, but rather looking for a universal understanding of geotechnical practices. Well, thank you very much for attention.
Thank you. Thank you very much, Pierre Schmitt. That was fascinating, lots of wonderful examples and lots of pragmatic decisions about what you need to do in order to design. I'm sure there are lots of questions. Would anybody like to ask a question?
Don't worry,
please do. No, he's finished inside 30 minutes. I was just sort of getting ready to do a 5-minute warning, having said he needed 35. But we've now got plenty of time to discuss, so I'm sure there will be questions. Who would like to start? Goodness me, we need to have... thank you very much. Please say who you are, just to make sure everybody knows.
Thank you very much for your lecture. I'm Luigi Callisto, University of Rome, La Sapienza. No, this is about material factor approach and resistance factor approach, because this is a very long story, in fact. My impression is that one should be clear about the goal of the analysis, because some analyses are really meant to be analysis for the ultimate limit state. In this case, perhaps we should be factoring in a finite element model, for instance, resistance of the soil. But if you want to allow for hinging in the wall, in fact, we should be using a single multiplier. So we should be factoring soil strength and concrete and steel strength by the same multiplier, because this is the way limit state is analyzed. What you did on the other end was an interaction analysis in which you used what is usually called a factor on the effect of action. And when you use an effect of action factor, that really is not an ultimate limit state calculation, but it's a solid structure interaction calculation in which you are trying to get displacement and internal forces, but you don't reach really, you don't model an ultimate limit states. So in my opinion, if you distinguish these two types of calculation, then the instance in which we should be factoring the effect of actions and the instance in which we should be factoring material resistance may become clear.
I understand what you said, but it is a debate that it is a debate that we had. Of course, I understand perfectly what you say, and I perfectly understand the logic of the MFA. It is to consider globally the ultimate limit state, including the structure. And this is why it is currently done using plastic hinges, because it is necessary if you want to optimize the design as well. So, but clearly the issue is that maybe some logic, but in fact in practice for concrete structures this is not practical at all, not I think authorized by structural codes. So that we need also to be pragmatic and consider cost efficiency and also working situation for concrete structures such as diaphragm wall. And also, I think it is maybe relevant. Of course, there is consider the ULS as a wall. In fact, there is ULS that is a general failure. Another philosophy consists in checking different ULS that are clearly identified and check them one by one, and check that finally they are relevant with each other. These are two philosophies. I think we cannot impose one of them to all countries in the world, probably, if we have many discussions about that. But what is important to notice, I think, why maybe in German was like France was that, in fact, we are not prepared. There are, in fact, many practice of design of retaining structures based on this, I would say, EFA approach, as you say. And now, changing now would clearly result in a significant increase in the cost of structures and in structural calculations. So pragmatically, we have to resist to do that. This is all I can say.
Competitiveness is important. Who'd like another bite at that? Another question, anybody? Your question was too amazing that your answer was obviously very clear. And come on, there must be some more interest, questions, anything worrying anybody? Any differences in style from different countries? We heard an Italian professor posing a question. And anybody else? No? Of course you may, Luigi. You can do a follow-up if you like. Sure. We're very happy.
Just since we have time. The use of subgrade reaction models, I think, is very much nation-specific. The way it is used in Italy really comes after the work of an Italian professor called Roberto Nova. And I think the basic difference is that when in a subgrade reaction model we simulate an excavation, we have an excavation stage in which we sort of model, initialize the stress rate in the springs below the excavation in a way that, in fact, passive resistance is reached below the excavation because of the stress paths. And then we allow movements of the wall. And this is done in order to cope with the distribution of passive contact stresses that you show in, I think, your first or second slide. So we must acknowledge that the bottom of the excavation is already in a plastic state when we excavate. And since this is a nonlinear problem, the way to initialize the stress state in springs really brings to a different result, because the result depends on the initial conditions. So I was wondering, how do you initialize the stress states of springs in the French practice and in the software that you are using?
In fact, we not initialize. I'm not sure I perfectly understood what it made in Italy, but the way we are practicing, in fact, the initial state is a K0. We just finally we know how to, we consider the value of the springs as independent, in fact, as a constant, in fact. And so, in fact, there is the calculation automatically considers unloading. Yeah, I know there were sometimes proposals to consider also the fact that there is an over-consolidation effect, in fact, due to the excavation, so that maybe we could, initializations could result maybe in higher values of K being considered, but in fact it is implicitly considered in the value we use. If you want, in fact, in practice, as you could see, our practice is just a very empirical one, derive values that are without asking too many questions about, we could also consider sometimes nonlinear springs and so on. We finally pragmatically try to match our databases of similar reference, and we use, in fact, the values that are shown to be in good agreement. But there may be other ways, of course. But if we consider different initial conditions, if we try to separate the effect of the over-consolidation due to excavation, we have to consider different values, of course, and there are maybe different ways to get to the same results. That is, finally, the result needs to be provided by geotechnical monitoring. So it may be different philosophies about that.
I'm Jean-Salençon. Just, it's not exactly a question, but coming back to one of your ideas, saying that safety factors could be considered as the limits of validity of models. Could you elaborate a little bit on this idea at the end of the lecture? Maybe you can illustrate it. I have no clear illustration or example. It is a thinking, because clearly what I try to show is that we can guess that there is a limitation of our models, and probably in relation with the overall displacement, because it is not always explicited. But when we made these calculations with active earth pressure coefficients, Coulomb, and so on, we consider that there is no overall displacement. So clearly, this assumption, how can we guess that it is realistic? And in fact, it is just a thinking. In fact, we have not really data to derive that. It's an idea that, of course, the safety factors should be an indicator. Is it relevant or not? I made the link with the fact that there are many discussions about the RFA that requires higher safety factor than MFA. And there is no logic, many discussions about that, and maybe, and I try to have the idea that maybe this could be explained that when we use traditional models, we need maybe to ensure that we are far away. It's just a thinking, in fact, that, but I have no precise idea. Obviously, we have to progress on that, because we had recently discussions with our German colleagues that which we share generally a philosophy. We are generally in good agreement. They use RFA as well, and they used traditionally safety factors in the range of 1.5 as we did traditionally, because in all soil mechanics books, this is the order of magnitude that were always proposed. And they told us that now they were, during the past years, and under the influence of Euro costs, trying to reduce their safety factors, and they told us that 1.25 might be enough to ensure that the overall displacement were negligible. We told them, okay, but if you have data, please, we are happy to share with you. But this was a few years ago. After that, I unfortunately retired, and I don't know where we are with the discussions. But obviously, this is subject to evolution. But it's just a thinking.
Time for one more question, short question, if anybody else would like to ask one. But you don't have to, so very good. So in that case, many, many thanks to
Thank you.
Pierre Schmitt.